the one that say, over the Gulf of Mexico, remember the one mixing the moisture is coming from the Gulf of Mexico, right? So the left side is IR and the right side is near IR. So this is the one I say, this is very dry because there are a lot of clouds here. This is the Hurricane Isidore here. So it's very, very dry, but it's not really dry. It's really above the cloud. The moisture is above the cloud. So you need to be careful. And then, and then you look at the color, probably not very, here it's more like a reddish, right? So you can see more moisture over the IR channel and much drier over the IR channel. So that's why, that area, even the rim, the upstream coming from ocean, and that's why probably won't be surprised if you don't have a rainfall over the area because the upstream is actually probably has drier virus because of the data itself. All right, so now back to here. We are going to talk about Emily, right? I don't know how many minutes I have. So this is the time period we are interested, right? Almost right after the Emily becomes category 1, and then we do about 54-hour simulation. And Emily is kind of interesting. It's a category 5 and has IO replacement to rapid intensification. So it's kind of a very interesting case. So this is a sea level ratio. So this is an interesting time we try to do. And unfortunately, we didn't assimilate any wind data. So usually you don't want to study from the very strong vortex. There's no way. You study from the analysis data at the time when the storm is really strong, and you don't assimilate any wind. I don't think you can pick up an initial vortex. All right, so we kind of pick up a time where it's almost like weak enough so we can start doing it. And so this is the time it's become category 1, and then through all the rapid intensification, and then they have the IO replacement, and then the second rapid intensification. So this is kind of a very interesting case. And this is the one who et al. 2008 for the case, then try to simulate wind data and also drop sound. So they studied a little later time because they have a wind information, so they can make a cloud a little stronger at the beginning because of the wind information. Okay, but then the whole thing is try to test different microphysics scheme. The winner is a Kessler scheme. Okay, so like Robin mentioned yesterday, it's pretty discouraging. When you have the most simplified physics scheme, and it's always the winner. And I probably not discourage too many physics developers here. Okay, so this is what they get. And Purdue, this is a scheme we took it from Purdue. I put it in the Wolf model. Actually, this is the very first one I put in the Wolf model. So I'm kind of interested in this one, and we put it into the all-hour simulation, and it's really weak in her case. So let's see what I want to do. So here, we want to compare what's the result assimilating the different total precipitable water, and we also want to see why it won't fail to simulate the Emily rapid intensification. Why? What's the reason? All right, so this is a configuration of model. It's really similar to Pooh et al. Actually, but we have a 30 kilometer, 10 kilometer, and then we have a Purdue here. She has a Purdue scheme too, and we have a Cambridge. She uses a George Grill scheme, and then we have the rest are all the same. Okay, so this is the configuration, and then the experience is very simple. Now there's no data assimilate MI, so this is IR data. And MN, this is MODIS near IR data. So this is IR and near IR. The A means AIRS. Okay. And we did a 6-hour data cycling. So whenever there's a data available, and we just assimilate every hour, and then do a 54-hour simulation straight. All right, let's see what's the coverage of the data here. So this is a MODIS IR data, MODIS near IR data, and the AIRS data. You can see the AIRS is kind of narrow a little bit, right? Okay, you can see a lot of data are kicked out. We have a lot of data here, but a lot of data here. We probably overreact, I think. We try to kick out all the cloudy data. It's probably we kick out too many anyway. But you try to be conservative at the very beginning. Now I'm going to show you the two group of data. You probably won't see which line is which line, but at least you see color, right? Just pay attention to the color for now. The green color is without GTS data. All the red color is with the GTS data. And unfortunately, in my experience with the GTS data, usually it's better, but not this one. The track becomes worse. So we decide to get rid of all of the simulation with the GTS. Only the GTS itself is pretty good, but everything with the GTS plus the satellite data is worse in terms of track. And we don't like the bad track for this case. Later you will know why. And the best one, actually the best track is with IR data. the best one is IR, which is the one that actually has the most intensification. All right, this is sea level pressure, the simulated sea level pressure. And you can see this is the magenta is the observed one. And you can see this is the IR replacement process here. And then they are all coming down and then start slowing for most of them. Only this guy, the one stands out, is the one that simulated IR data, which is probably not surprised because IR, statistically, IR has is moister than the other two data set, okay? This is compared to the force result, so this one after assimilate motion, they didn't really assimilate motion besides drop sum only. They didn't have any satellite data, okay? So you can see everything's pretty much the same, but this one's very weak and this one's going down. And this is a 10-meter wind, and after almost 24 hours later, you see this one's coming up, which is the IR data. And this is a 10-meter wind, the composite from the NOAA Hurricane Research Division. So you can see the asymmetric part pretty good. Everyone has this kind of wave number one of them. But this guy, which is the strongest one, the mean flow seems a little bit stronger than the others. But in general, this is still better than the other one. Okay, this is a this is not a 10-meter wind speed, okay. This is total precipitable water. So this is a non-case, the total precipitable water from the non. And you can see this is very dry band here. It doesn't look like, it doesn't look good, right? But well, Emily is category 5, so it seems it doesn't hurt the real Emily. You might hurt the simulated hurricane, but it seems not affect the real Emily at all. So this is what I want to give you a feature, what it looks like. And this is an increment. So basically, this is after you assimilate the data. What do you gain? What do you gain? So this is the one assimilated IR data. So minus now, this is what you have, and this is a track, the best track. And this is a near IR data minus now, and this is AIRS minus now. So let's take a look, just kind of briefly. You have a moist here. They are all kind of consistent, dry, and this is very, very dry because of the near IR guy. And this is moist here, and nothing going on here. This seems a little very dry. But this is more moist compared to the AIRS, right? And the dry, and this is moist here. Okay, so basically the main difference, if we just ignore this one, this is even weaker than the control arm. So just compare these two. This is the main one different, and this is the second one. This is more moist, and this is not that moist, and this is big moist, and there's nothing going on here. So we look at the moisture budget in the hurricane and see what is this is a number one, which is really the winner. Okay, a lot of moisture, we know that. But the moisture may be the chicken egg problem. Once it develops, it's going to suck in a lot of moisture, right? So it's going to have a lot of moisture. You won't be surprised. The second one we look at is like the shear. Shear is another one which might have some important role, right? So you see the number one here, this is IR. This is the one which has really decreased the shear to the